So today we are going to discuss Feynman diagrams. Feynman diagrams are entirely equivalent to what we've done over the last few lectures. So in the last few lectures, to remind you again, I'm trying to compute the scattering amplitude. We did that in 3 steps. LC reduction formula related this to correlation functions in the Heisenberg picture. We then used Dyson's formula to relate those Heisenberg picture correlation functions to free correlation functions, or interaction picture correlation functions, and relate the endpoint free correlation function to the 2-point function, or the propagator, using Wick's theorem. Okay, so we have, in principle, have all of the tools we need to compute scattering amplitude. The method we've derived is, in principle, enough to compute these scattering amplitudes, at least perturbatively. And logically, this is how we compute them. But Feynman came up with a graphical technique for skipping a bunch of steps. And in practice, the calculations using Feynman's diagrammatic technique are much easier than going through this. Logically, this is what we're doing, even when we're doing Feynman diagrams. But Feynman diagrams are easier in practice, and provides useful ways of thinking about scattering amplitudes or correlation. That's what we're going to do today. So today we will see how to directly relate propagator to the Heisenberg picture correlation functions using Feynman diagrams. Our eventual goal is to go all the way back here. I may be able to say something about this arrow today, but I won't be able to finish that. We'll finish up discussing how to use Feynman diagrams to compute the scattering amplitude on Monday. So Feynman diagrams, the basic idea is that we can represent lines represent Feynman propagators with lines. And what we're going to develop today and also on Monday are sets of rules for diagrams that we can draw that will represent perturbative calculation of some quantity of interest, whether it's a correlation function, scattering amplitude, and also rules for assigning complex numbers to individual diagrams. So we're going to develop rules for which diagrams to draw, and how to assign complex numbers to individual diagrams. So the rules will depend on which quantity we're calculating. If we're calculating different quantity, we may need to consider a different set of diagrams, and we might have different rules for assigning complex numbers to those diagrams. Those will all be related. There's analytic, but we have relations between correlation functions and the scattering amplitudes, the LC reduction formula, and the Feynman rules for these different quantities will tell us to consider different diagrams and to use assign different analytic expressions to individual diagrams. But that's just because these objects are different and are related in a way that we now understand. So we'll start. Our first goal is going to be to compute this, but along the way, it will be useful to let's start by considering our interaction picture expression for Heisenberg picture correlation functions. We know that correlation function can be written in the interaction picture using Dyson's formula. And so on the left-hand side, these are Heisenberg picture fields. On the right-hand side, these are interaction picture fields or free fields. For concreteness, let's consider a particular theory, particular interaction Lagrangian. We will consider, for most of today's lecture, called phi-4 theory. We're adding an interaction term that has field to the fourth power. And this lambda is known as the coupling constant. And so when we're doing perturbation theory, in a sense, we're doing perturbation theory in lambda. This is a small positive real number. For now, remember when we were discussing the LSE reduction formula, we said that it's not always consistent. Just add a term to our Lagrangian. We, in general, have to shift and rescale if we want to use the LSE reduction formula. I'm going to ignore that for now and just assume it's OK to add a term. We'll discuss renormalization more next week. See how we can fix that. But do keep in mind that beyond leading order in perturbation theory, this is not necessarily consistent. OK. So let's look at, for this theory, the simplest possible correlation function, which is the two-point correlation function. Two-point correlation function. Well, it will be a ratio of this numerator with this denominator. Now, let's consider those separately. Each of these is a correlation function in the free theory or a correlation function in the interaction picture, which we can compute using Wick's theorem. So we'll consider the numerator and the denominator separately. The numerator, first two terms in that numerator are just the free Feynman propagator. Then our next term, we need to expand the exponential, and I lambda over 4 factorial. Integral d for x. Let me call it y instead. Phi 1, phi 2, phi y to the fourth. I'm ordering. We can go to higher order. OK, So let's try to represent each of these terms with a Feynman diagram. And our basic rule is we're assigning a line, and let me label the points. Line from the space-time point x and y, be a Feynman propagator from x to y. And so lines, dots are space-time points. Okay, so our first term, numerator, is just using this rule. We can represent just by a single line. This is just the Feynman propagator. So nothing very interesting yet. Let's look at this next term. This next term has more going on. We have coupling constant, space-time integral, and we have 6 fields, our correlation functions, instead of just 2. So this term we'll leave out the coefficients for now. We can evaluate using Wick's theorem. So this term is going to be equal to the sum of all completely contracted contractions of these 6 fields. So there are contractions where I contract phi1 with phi2, and also the phi y's with themselves. So that will give. Okay, so that will give. If we look at the analytic expression first, we'll have a delta 1, 2. I'm going to introduce a new notation for this. I'll call this just delta 1, 2. And then 2 delta yy's. It also has a coefficient, because there are several terms like this. There's only one possible way I can choose to contract phi1 with phi2. The phi y's, there are several possible ways. You contract first with the second, and then I'd be forced to contract the third and the fourth, or I could contract first and the third, and second and fourth, or the first and the fourth, and the second and the third. There are 3 terms like this. I could also contract phi1, phi y, and phi2 with a different phi y. There are 4 choices of which phi y I can contract the phi1 with, and 3 choices for the phi2. And the last 2 phi y's are contracted among themselves. No choices. So I also have a term that's 12 delta 1y delta 2y delta yy. And the term here is not just this, but we also have a minus I. This should be minus, sorry, minus sign in definition of the Lagrangian. Integral d4y. That goes over here as well. Okay, so that's what we get if we look at it analytically. So the next question is, how can we represent that using Feynman diagrams? And well, this term here, this term has a propagator from 1 to 2, x1 to x2. It also has a propagator from y to y, and another propagator from y to y. So I can represent this term in white as this diagram. The term in yellow has a propagator from x1 to y, propagator from y to 2, x2, and also a propagator from y to y. So that's the diagram for the second. And given this, we can already guess what the Feynman rules are for the numerator. We're ultimately not so interested in the numerator, but the Feynman rules for the Heisenberg picture correlation functions will turn out to be closely related to the Feynman rules for the numerator. So let's write those down and try to understand those first. Okay, so the numerator is 0, y1, yn, exponential I, the integral of the interaction Lagrangian, is equal to a sum of diagrams. At leading order, I have the sum of all diagrams with our 2 external points. We have 2 fields here, 2 external points. If I added more fields here, I'd also have more points at leading order. I'm going to go to next to leading order and expanding the exponential. I get a factor of lambda, and I also get an interaction Lagrangian and an integral dy. So I get one extra point that's in the interior of the diagram. It's not an external point. This y always shows up in the interior. There's never a single line that extends from y. It's always 4 lines, 4 fields there. And if I went to higher order, I could get diagrams with more internal points. These are external points. An internal point. And note that these are the only 2 diagrams I could draw with 2 external points and 1 internal point. I want to draw other diagrams that have 2 external points and more internal points. I need more vertices, more internal points. So this numerator is equal to the sum of all diagrams with n external points. No, there's some caution here. It's writing this is equal to. Remember, we discussed last time that this was actually an asymptotic series in general. This doesn't necessarily converge. But nevertheless, finite truncation of this gives us a good approximation. Okay, so that's that's the rule for which diagrams to draw. We just draw all the diagrams for the numerator. So very, very simple rule. Then, so that's only part of using Feynman diagrams to compute quantity of interest, is drawing the diagrams. The next step is to associate complex numbers with those diagrams. So there are a set of rules we can use to, for a given diagram, associate an analytic expression for it. The first rule is that lines are associated with propagators. That's how we determine what diagrams to draw. And so we just use that backwards to get the analytic expression. Our next rule is rather trivial for the cases we'll look at in this course, but I'm going to write it down anyways because in QFT1 you'll deal with field to spin, and there'll be a rule here. So just so you don't forget that, I'm going to write it down. External points are associated with a factor of 1. So these are all multiplicative factors. QFT1, this rule will change. Our third rule has to do with the vertices. So in this theory, we have a single type of vertex because we have a single interaction term here. And for every vertex in our analytic expressions, these diagrams have vertices. They have factors of minus I lambdas and integrals over the internal points. This diagram has no such vertices and no factors. The vertices, you can think of it as these divided for operators, always come with factors of lambda and integrals. So that should be reflected in our Feynman rules. And so for this vertex, we're going to associate a factor of minus I lambda integral d4y. Note there's no numerical factor in this rule. I'm only including the lambda and the integral and the I, but not the 4 factorial. This rule, and that's intentional, and I'll discuss that when I get to the fourth rule, why. But this rule depends on the theory. So which vertices are allowed, and what the coupling constant associated with each vertex will depend on our choice theory, or in other words, in our choice of interaction Lagrangian. So this rule is specific to phi-4 theory. We'll consider other examples in this course and future courses. And our last rule is to divide by the symmetry factor. And this requires some more explanation, but this is where I'm accounting for the 4 factorial. So there are two equivalent ways to determine the overall numerical factor associated with a given diagram. One is the Wick's theorem counting, which I did before. Counting the number of Wick contractions, that gave us the 3 and the 12 here. That way works, and it's equivalent to the way I'm about to explain. I encourage you to do it both ways. First few times you're drawing Feynman diagrams and trying to determine the symmetry factor just to make sure you understand the counting. After some practice, this other method will be faster. It won't necessarily be faster the first few times you try it, but for nearly everyone, this is faster. stretchy geeks. And the symmetry factor, I'm going to define to be the number of ways to map diagram to itself with the external points held fixed. Another way to say this, equivalent to what I just said, but is it's the order of the automorphism group. That something you're familiar with. So let's look at an example and see how this works. So we had two diagrams over there. Let's look at the first one, this diagram. Or the second one, sorry. The second one's easier. Second one first. This diagram. So this diagram, there's only one. The symmetries I can do to map this diagram to itself is I can flip the ends of this internal line. This has a factor of 2. I can either flip or not flip ends of the internal line. Symmetry factor here is 2. That comes from swapping the ends of the line from y to y. And the fourth Feynman rule says that the overall numerical factor associated with this diagram is 1 over the symmetry factor, 1 over 2, which is 12 over 4 factorial. This is the number of Wick contractions. That we just determined 2 minutes ago. And this 4 factorial comes from the normalization of the interaction, Lagrangian. And the claim, although I'm not going to prove it, is that these two ways of counting are always the same. Assuming we normalize the interaction Lagrangian in the following ways, that we have a term, let's say that if L int is a field of phi to some power n1, second type of field phi power n2, and a third type of field rho to some power n3. I'm going to normalize it by dividing by n1 factorial, n2 factorial, and 3 factorial. And put a coupling constant. That's this is completely standard. This is basically always the way we normalize interactions. And one reason to do that is so that this other counting works. So if this were our interaction Lagrangian, we would not have this term. Instead, we would have a vertex with n lines of type phi and n1, and 2 lines. I'm drawing with a different type of line, big phi, and n3, which I'll draw with yet a different type of line. Particles, lines going into the vertex of type rho. This would be associated with a factor of minus ig rho d4y. Okay, and let's check that this works for our other diagram. Before we check, let me just give you some possible types of symmetries to look for. You can look for swaps of ends of lines, ends of internal lines. You can also look for swaps of the internal lines themselves. And we can also look for swaps of entire subdiagrams. Some of our diagrams have several different pieces, like this one. Sometimes there's symmetry associated with swapping them. Okay, so let's try to check that this works for our other diagram. Okay, so what's the symmetry factor of this diagram? If you have part of the answer, if you can identify something we can do to this diagram that leaves it invariant, you can build up the answer.
Is it 4? Because you can like flip vertically and flip horizontally and leave the 1 and 2.
Okay. Yes. So thank you, Mary. So one thing we can do is we can swap these two lines. So that gives us a factor of 2. You identified another symmetry, which is swapping it over, or reflecting it over, correcting it or rotating it over a vertical line. We can think of that as swapping the ends of the upper internal line and the lower internal line simultaneously. That's something we can do, but there's more. We don't. Can anyone identify what?
Why should they be simultaneous? I mean, you could swap the ends of the upper one, and that's 2. Swap the end of the lower one, so that's 2 is 8.
Yes, good, Ali. So yes, so we can do those independently. We get a factor of 2 from ends of the upper line, and another factor 2 from the ends of the lower line. And our overall numerical factor associated with this diagram is 1 over s. 1 over 8 should be equal to the number of Wick contractions, which is 3, divided by 4 factorial. So again, it works. For this example, it's not so clear why the symmetry factor is easier with practice. Part of the reason is that the diagrams we're considering here have large symmetry factors, but in practice, most diagrams have s equals 1 or 2. There are exceptions, but that's part of the reason why it's useful to do this, because nearly all the time you will have so many different ways you can map the diagram to itself.
Well, you defined your Lagrangian as a 5 to the power of 4, so that would induce a lot of symmetries. So are you saying that, I think that was the point, because when you have 5 to the power of 4, you have a lot of symmetries in your expansion. So, and does that also imply that, for example, your Lagrangian is mostly proportional to 5 and 5 squared? Well, I'm missing something.
It's true we chose a particularly simple Lagrangian. That it's part of the reason why we have large symmetry factors here. We're also looking at just the numerator instead of the Heisenberg picture correlation function, which we're mostly interested in. And as we'll see, there are a smaller set of diagrams that contribute to the Heisenberg picture correlation functions. So that's also a partial answer. And charge, so we're dealing in neutral particles here. Charge, if we're dealing with charged particles, the lines will have arrows on them. When you're mapping a diagram to itself, you need to account for the flow of charge, and the fact that the arrows are directed will tend to mean there aren't so many symmetries.
Thanks.
Becky?
Is that why we can't swap the line from between 1 and y? Why we can't flip that?
We can't. Yes, we need to hold the external points fixed. So if I swap the ends of this line from 1 to y, then the end that was attached to 1 is no longer attached to 1. So I've changed something related to the external points. In other words, I can tell you which end of this line from 1 to y is which by just making a statement involving the external points. I can say this end is the end that's attached to the external point 1. For the two ends of this line from y to y, there's no such statement I can't say. I can't say that this end, no, I've drawn it on the blackboard, is closer to 1. But topologically, there's no way I can say that it's a distance of 1 line away. That's true of both ends of that line. So there's no statement I can make that distinguishes those ends of lines just by referring to external points and topological features of the diagram.
So mathematically that makes sense because we want to get the exact same picture that we had before. But is there any physical intuition that you can give as to why we choose the external points to be fixed? I know mathematically it makes sense.
Well, so the internal points are integrated over. So the external points are not. So that they're treated very differently mathematically. Okay, so that's the numerator. Ultimately, in most cases, we're not really interested in the numerator alone. It's just a tool we use to calculate the full Heisenberg picture correlation function. So let's examine the denominator and then combine our results to get the result we're interested in.
Sorry again. So when we're doing the diagrams, we'll get terms like the one with the ribbon on like y, the thingy, and it's sort of an internal process where just by looking at, as you said, x1 and x2, there's no way I can make sure that that thing existed in physical process. So and somehow it shouldn't contribute to the expectation value at the end, right?
Yes, we're going to see that cancels out. That's what we're going to discuss next. But yeah, your intuition is absolutely correct. That this diagram and some there's a disconnected piece. So this it's reasonable to question whether this disconnected piece affects the propagation of the particle from x1 to x2. And we'll see it doesn't. Okay. So let's look at the denominator, which is this piece. And, well, in a sense, we already understand it. It's exactly the same as the numerator, just with no external points. So this is equal. Yeah. Thank you, L. Thank you, Ellie. L in there. So this is exactly the same as the numerator, just no external points. So this is equal to the sum of all diagrams with 0 external points. Let's draw them. So the first one is that there are no such diagrams with 0 internal points. Although if we expand this, we still have a 1. So we'll have a 1 plus first diagram corresponding to the linear expansion of this term. Then we have two vertices. I can draw a single disconnected diagram like this. one diagram. You can also draw a connected diagram with two vertices. Like this, or like this. And there are no other diagrams I can draw. Two vertices and no external points. There are more I could draw with more vertices. So at second order perturbation theory, this is the denominator. And the denominator came from an expansion of the exponential. It's reasonable to guess that there's some way we could write this as an exponential of something. Expanding an exponential, writing the exponential in a different way. And, well, our second order expansion already gives us a hint. This diagram looks like the square of this diagram. Two copies of this. So natural guess, which turns out to be correct, is that the denominator is the exponential of the connected vacuum diagrams. I'm not going to prove that, but just do a consistency check to make sure it makes sense that we do, in fact, cover this diagram with the correct coefficient if we expand this exponential out. So explicitly, this is the exponential of connected diagrams. The only connected diagram with one vertex is this one. Two vertices, it'll be these two diagrams. This one is not connected. It has two connected components. And so we get a term like this from the second order expansion of this exponential. So we have this diagram. It's a single diagram. And we want to compare that versus the term that comes from the second order expansion, which will have a 1 over 2 from the second order expansion of the exponential times this diagram squared. This is a single diagram squared. The symmetry factor of this diagram is the same as the symmetry factor of this diagram. This part didn't contribute at all. The symmetry factor here is 1 over 8. So here we have this one. This term, we have 1/2 and a 1 over 8 squared. One over s. For this term, we have, this is a single diagram. So we have a symmetry factor of 8 for each subdiagram. We also get an extra factor of 2 from swapping the diagrams. So the symmetry factor is 1 over 8 squared. It's 1/2. And this half comes from swapping the diagrams, swapping the subdiagrams. So our guess passes that check, and in fact, you can show that it's correct.
So when we swap subdiagrams, they have to be identical?
That's right. That's good. Okay, so let's combine our results, the numerator and the denominator. So denominator, denominator we have already. The numerator, well, we also have these types of diagrams in the numerator. We saw that already. This term here was the product of a connected component with two external points times a connected component with no external points. And we can construct a general term. In general, if we're looking at the two-point function, it will have one connected component with 2 points. So it could be this or this or some higher order terms. And then it can also have any number of connected components with 0 external points, which is just the denominator. Be 1 plus this, this. So this is equal to you can write this as the part with external points times an exponential of the connected vacuum diagrams. And so this part cancels between the numerator and denominator. So we're left with this. That's just this part. No vacuum subdiagram. So our Feynman rules for the Heisenberg picture correlation function are very similar to the Heisenberg picture, or to the Feynman rules for the numerator. The only difference in the Feynman rules for the numerator versus the Feynman rules for the correlation functions are that Feynman rules for the correlation functions consider a smaller set of diagrams. So there's the same warning about convergence, but we're only considering the sum of all diagrams.
Was that Cato Kicks omega?
Yes. With n external points. And no vacuum subdiagrams. Otherwise, nothing changes. Okay. This is a good place to take a break. Resume in 5 minutes. Okay, so we've written down the Feynman rules for the correlation functions. Those are interesting objects we'll study further in future courses. In this course, our main object of study is going to be the scattering amplitude, though. So let's try to write down Feynman rules for the scattering amplitude or matrix element. So before we do that, I just want to speak more precisely and clarify what I meant by some of the different ways I've been referring to the scattering amplitude. The scattering amplitude is what we've been studying so far. This is what shows up in the LSE reduction formula. Yesterday, I spoke about, this is sometimes called the matrix element. That's almost true, but up to a normalization that I want to explain now. So physically, we expect this scattering amplitude is 0 unless energy and momentum are conserved. So that statement is true regardless of what theory we're talking about, regardless of the form of the interactions, the types of particles we have. So they're in this scattering amplitude, we expect that there's a momentum, for momentum conserving delta function, which is universal and in that sense, not so interesting. So it's convenient to factor that out. And we can define known as the matrix element. It's related, very closely related to the scattering amplitude. We're just pulling out a momentum conserving delta. So it's sum of the initial form momenta minus sum of the final form momentum. And what's left over is the matrix element. Which depends on the initial state and the final state. And there's a factor of I here. It's a convention. So we expect this delta here on physical grounds, and we're going to see it pop out of our calculations. We can use LSE reduction formula and our knowledge of Feynman diagrams of the correlation functions to compute this. And we're going to see delta functions like this pop up all over the place. And so when we write down our final Feynman rules, it'll be easier to write down final Feynman rules for them. Ubiquitous momentum conserving delta.
The scattering amplitude is telling us the probability for the state to go from I to F. So the Dirac delta is only in the momentum space, right? Because it should be a real thing and not something which we need to integrate. So this is in the Fourier space.
Yeah, so we're assuming that our initials, in the LC reduction formula, we assume that our initial state and our final state were momentum eigenstates, particle number eigenstates. If I do a scattering experiment and I specify the initial and momentum two particles, the probability amplitude that they'll go to a exactly specified final state will be infinitesimal. Experimentally, we'd have to integrate over some finite region of momentum space for the final particles to get something finite. And so the fact there's a delta here is not a problem.
Be integral over momentum space and then this
yeah, so experimentally, what we'll measure is never this for a fixed f. It would be some integral over maybe some small region of momentum space.
Sorry, what does the semicolon mean in front of the matrix element?
This is supposed to be an I.
Oh.
Sorry.
Thanks.
Square root of -1. It's conventional. Yes. So this is what we expect on physical grounds. Our calculations better give us this delta, and we'll see it come out. Okay, so just to remind you, the LS reduction formula. Let's again, focus on the 2 to 2 scattering case. Integral product for xj by lambda j Okay, so I'm using the same notation as before. This is a Laplacian with respect to x sub j, like days ago. This product is over this part. And we know how to compute this using Feynman diagrams. Our goal is going to be to try to see what that tells us about which Feynman diagrams we should draw and what factors we should associate or to each part of the diagram. We already, just looking at this diagram, got some expectations. So this is a momentum space. Doing a Fourier transform here. So it's natural to expect, instead of having a line associated with the Feynman propagator and position space, we'll get the Fourier transform. That expectation will be out. One key feature of this formula is these Klein-Gordon operators. So these are going to play a key role in determining which diagrams to consider and what rules we need to use to write down the matrix element associated with those diagrams. So this is the key feature of this formula. And I just want to remind you that in this formula, when we derived this formula, we did not specify a Lagrangian. We did not need to make any assumptions about what form our Lagrangian took. And this mass came out from using the relativistic dispersion relation, E squared is K squared plus M squared. This is the physical mass. And that this is will be essential to keep in mind. I probably won't get to a full discussion of this point today, but we'll come back to that on Monday if I don't get there. Yeah. So again, our strategy is going to be to look at some simple examples and see if we can guess formulas, and we'll try to get some understanding of where the rules come from by doing that. So let's look at, again, we're going to consider the theory where by 4 theory. And we're going to have non-trivial scattering. We need to have at least 2 particles in the initial state and 2 particles in the we'll look at the 2 to 2 scattering case. The relevant correlation function is the 4-point correlation. Okay, so let's start by drawing the diagrams at leading order for the 4-point correlation function. So at leading order, there are diagrams I can draw with no vertices, and there are 4 such diagrams. I can draw a diagram where particle 1 is connected to particle 3 by a line, or particle 1 is connected to particle 4 by a line, or particle 1 is connected to particle 2 by a line. So for the correlation functions, the role of the orientation of the diagrams doesn't matter very much. When we're talking about scattering, it's convenient to have the initial particles at one part of the diagram. I've drawn in anticipation of the fact that we're computing the scattering amplitude. I've drawn the initial particles 1 and 2 at the bottom. So I'm using the convention where time is going upwards. And this is this diagram. And note that I've kept the external points at the same point, at same location in each diagram, and changed the way I've drawn the lines. I encourage you to do that. It's easier that way you can tell at a glance if the diagrams are the same or different. This diagram is entirely equivalent to a diagram if I switch the labels 3 and 4, but then it's hard to tell. The physics and math doesn't change, but just it's easier to do it that way. Okay. Okay. So let's see how these diagrams contribute to scattering. What do we expect these diagrams look like? We're thinking about this as telling a picture. This is a crude way of thinking about it, but if you think about this as a picture, what these diagrams look like is this is particle 1 propagating to become particle 3 with no interactions, 2 to 4. These are identical particles, so they can go to that. And this diagram looks very strange.
Sorry, just to clarify, this is like the 0th order terms?
This is 0th order, yes. So there should be order lambda terms I haven't considered yet. But we'll consider those in a few minutes. Okay, so to go from correlation function to the amplitude, I need to do a few things. I need to apply line Gordon operators, and I need to do a Fourier transform. So let's look at this diagram. You note that the 1-3 part doesn't really talk to the 2-4 part. Consider those separately. Got a Klein-Gordon operator respect to x1 and respect to x3 and Fourier transforms, and they're all independent. There's no terms that mix 2, 3, and 4. So I'm just going to consider part of this diagram. And let's see what notation I used. I'm going to call this f x1 minus x3. And it's just going to be the 1 and 3 Klein-Gordon operators. Acting on the 1 and 3 part of the expression for this. So this is just delta 1, 3, delta 2, 4. So this is a part of the LSE formula. I'll deal with it parts separately. It's a long formula. Okay. So what the LS bed reduction formula tells me to compute is d4 x1, d4 x3 of f of x1 minus x3. And note that I've written it as a function not of x1 and x3 separately, but just as a difference. That comes from the fact the Feynman propagator only depends on the difference in space-time points, not on the 2 space-time points separately.
Sorry, Dan. Shouldn't there be the propagator 2, 4 in the formula?
I'm not writing down the whole formula. You can take this to be a definition. To get the full thing, I'll need to consider the 1-3 part and the 2-4 part. Do those separately. And I also have exponentials. And did I get the signs right before? Sorry, I missed the sign here. This should be plus. And then we have the exponentials e to the I x1 p1 minus x3 p3.
Why was it plus? The last time you wrote it was
Was it a minus? Okay. Okay. If I wrote minus last time, or if it says minus, ultimately what will matter is the relative sign, the sign between the initial. If I have a plus or minus missing here, it's not going to affect it. Okay, so this is part of the LSE reduction formula. It's the part that depends on 1 and 3. And to analyze this integral, I can do a change of variables. I can write it in terms of x1 minus x3, x1 plus x3, and p1 plus or minus p3. Those variables will be, I can call x1 3 bar, and the same for p's. I'll put a factor of 2 there. And after this change of variables, I get integral d4 1 3 d4 x bar 1 over 2 to the 4 from a Jacobian, and then I get f of x1 3 bar and exponential of I x1 3 e1 3 bar minus 1 3 bar 3. Plus. And so what I'm left with, this is a Fourier this is telling me to take a Fourier transform of f, and there's no dependence except for the exponential on x1 3. So these are two independent integrals, x1 3 and x1 3 bar. I'll get Fourier transform of x1 3. So we can write this as x of e1 plus minus p3 2 plus bar here. And then the Fourier transform of 1, which is going to give me a delta 2 pi to the 4th times a delta of, I missed a bar somewhere.
Why is f only a
Bar. No, the bar should have been here before.
is f only a function of x bar 1 3? It's x comma 1 minus x3, wasn't it?
So this f depends on x1 minus x3 because
I thought it was a comma there. Wasn't there a comma?
no.
Oh,
No, this is because delta 1 3 depends only on the difference. The Feynman propagator depends on the difference between the spacetime points, not on the spacetime points individually. That's a consequence of translation invariance. Translate our whole system, that doesn't affect.
Why do we have the 1 by 2 to the power 4?
Jacobian. And so the x13 bar integral will give me this Fourier transform of f. But the x13 integral will give me a delta of P1 minus P3. So this is an energy and momentum conserving delta. We expect to get energy and momentum conserving deltas, general grounds. This is a stronger energy and momentum conserving delta. We expected to get one that just said that initial form momentum is equal to the final form momentum. Here, this is the momentum of just form momentum of just one of the initial particles equal to one of the four. So this diagram does what we expect. It says that particle 1 becomes particle 3 at the end. And there's no change. This diagram doesn't represent scattering. There's like free propagation. This is no scattering. I looked at the other part of the LSE reduction formula. Be the same as that with 1 replaced by 2 and 3 replaced by 4. I'd get the delta that conserved that sets the energy momentum of particle 2 equal to energy of particle 4. The same is true for this diagram. So these diagrams are no scattering. And they also have 2 deltas, which is more than the one we expected. This weird diagram, the weird diagram, 1, 2, 3, 4, will be proportional to a delta of P1 plus P2 and delta of P3 plus P4. So that's weird. And in fact, we can argue, so this is a consequence of the argument we just did, using the LSE reduction formula. We can argue that for massive particles, the arguments of these deltas are never 0. Because for massive particles, we have P1 naught plus P2 naught. In other words, the energy of these 2 particles has to be at least m in each case, which is 0. So these arguments of these deltas are never 0, so which means this diagram vanishes.
Two questions. Will we not have pi to the power 4 here because we have 1 by 2 to the power 4?
So I could write this as 1 over 2 to the 4 with a over 2 here. I've changed the deltas to get rid of that again.
Also, another question, can we think of this as at a fixed point of time, we are going from 3 to 4, so it's like traveling with infinite velocity, so this diagram is vanishing.
This diagram here? Yes, this diagram is unphysical. We have 2 particles in the infinite past. Yeah. Okay.
The argument that sums the energies and says is positive, does that assume our Lagrangian won't have negative energy states?
We're assuming that the physical energies that we can measure at minus infinity are at least a mass. The energies are k squared plus m squared. If k is 0, ek is m, and if k is non-zero, then these are greater than.
Yes, but when we solve for the spectrum of the Lagrangian that we specify, what if we get negative states, negative energy states? Then that argument wouldn't work, and those things would contribute.
That's right. We're assuming here that there's a gap in the spectrum, that there are weakly interacting particles in our theory. And this feature is general. If we have disconnected diagrams, we'll have one delta per connected component. Which means we'll have more deltas than the single delta we expect, at least for fully connected scattering. And so it doesn't mean that the disconnected diagrams are zero. Some of them are, some of them won't be. It doesn't mean that they're uninteresting. For 2-to-2 scattering, if we have disconnected diagrams, they are uninteresting because disconnected diagrams will just have two pieces that represent free propagation. But if we deal with higher point correlation functions or scattering with more particles, there can be disconnected diagrams that do involve scattering. But what it does mean, if we have extra deltas, is that there is no interference between fully connected and disconnected diagrams. And so we can consider them separately. And the fully connected piece is the most interesting piece. It's not always the only interesting piece, but it's the most interesting piece. For 2-to-2 scattering, it is the only interesting piece. We want to determine how these scattered particles interact. So these disconnected pieces, in a sense, are a trivial part of the S matrix. That it's possible that the initial state can evolve to the final state with nothing happening. That's not so interesting. And the reason that there's no interference is because there's two cases. In one case, the extra deltas, the arguments of the extra deltas are non-zero, in which case the disconnected diagrams are zero. These diagrams will contribute to the matrix element, but this diagram will be zero unless P1 equals P3. And so for P1 is not equal to P3, this diagram is just zero. If P1 is equal to P3, then this diagram has an extra delta, so it's infinitely larger than the fully connected components. So either this is zero or it's much bigger than the fully connected points. So there's no interference in either case. So we can consider these diagrams separately. And for most purposes, we will restrict ourselves to the fully connected diagrams because those are the most interesting diagrams. Okay, so we'll resume and write down our Feynman rules for matrix elements next week, and also reconsider our assumption that we could just write down any Lagrangian we want, and we'll start to discuss renormalization and how this Klein-Gordon operator affects the diagrams that contribute. That's where we're going. So as a reminder, I do have office hours tomorrow. If that books up or you want to come speak with me another time, you're welcome to drop by or send me an email. Set up a time.